which is to keep it short. So I'll try to keep it short, talk about a few different things, but also maybe plant some ideas for discussion along the way. So feel free to avail of those as we go through. And can everybody hear me in the back? Okay. Feel free to avail of those as we go through. And of course, also save some at the end if you like. So the title is this idea of how to execute quantum gate operations, but really in a dressed frame, right? Where we actually generate entanglement by going to some other frame of reference. And that has many advantages, as you'll see, in terms of changing the frequencies of the qubits, changing the strength of the interaction, et cetera, parameters which may be rather fixed if you stay simply in the laboratory frame. And I changed the title by one letter. This is not me making a typo, which has happened to me once in the title of a talk, but I really do want to talk about things that have more than two levels. And that allows us to actually go ahead and engineer a different type of interaction. I don't think it's me. These are the folks that have really worked on the 3 manuscripts that I'll talk about, and I think you'll have access to the slides. So if one wishes, you can look up all the details in the manuscripts later on. So I just wanted to give sort of a very high-level idea of where in the phase space is this talk, because we've been hearing some wonderful talks in the morning about different operations you can do with the basic building blocks of, let's say, quantum optics or quantum information tools in the superconducting domain. And those are really oscillators, nonlinear media, and photons. Yes, and we treat microwave photons on the same footing as optical ones. It's quite important to me to do this. So if you think of, very good. So in terms of parametric amplifiers, one thinks about something that, let's say, is a standing wave type of device, something that doesn't have any physical length or what have you, where you think of a nonlinear cavity that allows you to mix or transfer energy to a signal, let's say from a pump. And that can be translated into the circuit domain by having some type of nonlinear oscillator. Maybe.
Is there feedback coming through the mic? Maybe here.
If I turn off the mic, I think you won't hear it on Zoom, so that's probably not good.
Yeah.
Wow.
Yeah, I think it's just the computer in this.
Make sure this is.
Yeah, maybe we can mute it.
We can make sure we don't have anything here, but it's muted. All right, let's try again.
Maybe I can also.
Very good. That's cheating. That's experimentalist. Good. So the idea then in this particular medium is to take a circuit which now has this nonlinear oscillator behavior, and it'll give you the same thing as a parametric medium or chi2 or chi through nonlinearity in the optical domain. The challenge, of course, is that you need to get photons in and out of this cavity, the same challenge that's here. So the bandwidth in traditional devices will be limited by how this interacts with the outside world. If it's a simple cavity, it's the kappa or Q of the cavity, which will set that. If you wish to design a more complex circuit to impedance match that, we can with an array of elements. And you can use fancy functions. We heard Jacobi elliptical functions in the morning. You can use Kloppenstein functions, Chebyshev polynomials, all things that esoteric mathematicians worked out many years ago to get more signal in and out of this. The other approach is to think about something that has more of a spatial or itinerant character, where it's more distributed. In the optical domain, you can take a spool of fiber, erbium dope it, and you'll get an optical parametric amplifier. As your photons go through this fiber, you will have this gain process happen. And as our session chair told us, it's quite important to actually match both the momentum and the energy through this process so that you have an efficient transfer. And that requires some different engineering of the dispersion relations, say, in such a device. And we have done this in Josephson junctions. Others have done this in Josephson junctions. And it seems like a nice way to get broad bandwidth in your device. There are many tricks to doing that. And I'm happy to talk about that if you wish in the discussion session. Some folks asked about that, but I just want to drop it as a topic of discussion that we may have after 25 minutes. But really what I want to focus on in this talk is actually reversing this idea. So what we're doing here is using a nonlinear oscillator to have a photonic interaction to enhance the amplitude, let's say, of photons. And the figure of metric here, for example, is what's the efficiency of your process? What's the noise temperature? How much do you add? How close are you to the quantum limit, which is also very interesting in traveling wave devices. But I want to look at the opposite problem. What if I actually want to couple the nonlinear oscillators using these photons? Right? So it's the same kind of elements, but now I'm doing kind of the inverse problem. And the same elements will still come in. This idea of parametric driving, of coupling, of Raman transitions, so on and so forth, all of these things. But that's really the subject of the talk. And what's very interesting is we talked about the different communities that are coupled. There is sort of the microwave photonics people, the optical photonics people, but there's also the quantum information dimension to this. Because many of the routines and processes that one has in this qubit or quantum computing world actually intersect with these physical processes. And it's a very good way to benchmark how good these processes are. So for example, when we answer the question of how good is a quantum gate, you learn something about the transitions that are happening in your system. So I will sort of show you a little bit of that as we go through it, drop a few things in that language along the way as well. So here are two qubits pictorially shown here. So that's basically an oscillator. It's nonlinear. In this particular case, it's a Transman qubit. And in fact, what I want to do is think about how to couple these two nonlinear oscillators, the two physical pendulum, if you like, together. And I have a box in between, which is a coupling circuit. And the idea is that there are many coupling circuits you can have. There are some that I know that I've forgotten to put here, and there's some that I don't even know that I've forgotten to put here. So please don't take offense if your favorite coupling scheme is not here. But some of the simple ones that you can use is just to have a capacitor, right? Just to have a fixed coupling between your two pendula. You can have a resonator, so it only couples at a certain frequency. You can have a waveguide, and you can see how this is similar to the previous slide that I had. You can use things that are narrowband or broadband. You can have things that are tunable some way, as a squid, a qubit, or some other circuit, and so on and so forth. And the typical idea is that you'd like to turn this coupling on when desired so that you can do a gate for some very short period of time. But then you also want to turn it off because you want to manipulate the levels in these two oscillators independently. And that, of course, makes things a bit challenging. So one way that you can approach this problem is to tune the elements. Right? So you can go ahead and actually, in the rest frame of the laboratory, try to get these levels to be in resonance sometimes and not in resonance in other times. So you can tune via magnetic flux. So superconducting circuits arranged in loops will tune with a magnetic flux. You can use the Stark effect by applying electric field that will shift the frequencies of your atoms, say in the same way that a physical atom is shifted. And then there's also a slightly different, a rather different approach, I would say, which is to keep everything fixed, but add more photons in the problem in higher order processes. So fixed frequency of resonant elements with parametric drives is a tremendously useful way for doing this. And Professor Schuster and others have really mastered this over the years. And we use this as well in many different ways to great success. Also, Michael Hattridge here has done this. Never angered the Texans. So the other thing that I'm going to talk about today is if I actually periodically drive the circuits, then I will go to a different frame of reference. And then I can do many more things. Okay, in fact, I can go beyond simple parametric interactions and actually have Raman transitions and things which are also quite powerful. So that's really the corner of phase space that I want to talk about, but I wanted to plant it within the other corners that were being discussed this morning. Okay, so let me just go through this animation here. As you increase the number of levels in your oscillator, right? This is typically the quantum optics situation. You have a harmonic oscillator with many different levels, and they all participate. In the qubit world, it was qubit, right, with only 2 levels. But in fact, more recently, we've gone to things that are Qudits, and the utility of that for quantum information science is that your Hilbert space then will maximally grow as not 2 to the n, but d to the n, where d are the number of levels that are there. But again, this is kind of nice because now I have more generalized oscillators, right? And this physics of how to couple nonlinear oscillators is very applicable to an n-level system and not just a qubit system. So there's that duality there. So the axis that you can have is the dimension of your oscillator, the number of elements that you have, and the anharmonicity. Are your oscillators very nonlinear or are they weakly nonlinear? And in fact, I wanted to show in this that you could actually span the gamut here of oscillator devices that are very weakly nonlinear. So they're almost a bosonic type of system with the Kirkhat qubit, for which we have the world expert sitting here. And then you can go to things which are truly flux qubits or things that have, let's say, the 0-1 transition, the first level of your oscillator being a few gigahertz, and the next one being like 20 gigahertz, right? So extremely nonlinear in that case. So these are all elements available to you, and different ones will come into different uses along the way. The challenge then is to have some kind of operations that couple these or entangle these oscillators in a way which is very efficient. You don't want to entangle one part of your Hilbert space at one time, one level at one time. You'll run out of coherence very rapidly. And also to fully entangle them. See, quite often in our field, we had many of these levels, but you only entangle some small subspace. Right? That doesn't give you the D to the N utility that you have. That's still a qubit with a whole bunch of other levels that you don't control. So the goal is to actually go ahead and have this maximal entanglement in the system. And also to look at things that are many-body, not just entangling two things, but entangle n objects or n oscillators at the same time. So those are the themes I want to look at. Okay, so just a word of what the physical system is. It is a transmon qubit, right? And the idea is just a Josephson junction shunted by a capacitor. It has energy levels of this flavor, and you would write the Hamiltonian, let's say, of this more generalized system like this. You would have the resonator here, and of course, you have the projector for the different states. So this is just, for example, the projector of 0, 0, 1, 1, so on and so forth, for all your states that are here. And then you have some generalization of this Jaynes-Cummings term, which shows that you can swap an excitation from this n-level oscillator to your photonic field and vice versa. The point of this slide is if I couple this object, which now has n objects, to a cavity, I'm going beyond the usual Jaynes-Cummings type of Hamiltonian that's there. And in fact, if I go to the dispersive limit, I can still go ahead and write a dispersive shift for each one of these Qudit states. And in fact, here's an experimental measurement in the IQ plane of the phase response of this Qudit system. And you can see I can pick out in this particular case 4 states very easily. So this follows very easily from this, from the extension of the basic Jaynes-Cummings model. And the fidelity of the readout is pretty good for all of these states and can be made better also. So the interactions that I want to talk about going forward are this Kerr interaction, right? We saw this in the previous talk, and that becomes a cross-Kerr interaction now that you have multiple levels. And then there are more exotic things which I can cook up, which are exotic at least in the superconducting domain, not in, let's say, cold atom physics, but typically interactions that are similar to the XXZ Heisenberg interaction, right? And that's actually not an easy one to get in superconducting circuits. We are able to do this very easily now in the rotating frame or this not laboratory frame, and also to show you Raman interactions that are there, that are again very common in ion traps, say. Okay. I did want to drop this note here. Folks that are coming from the quantum information side will say, well, look, we have all of this machinery for qubits, and it's all based on the poly group and poly operators. Right? You have X rotations, Y rotations, Z rotations, so on and so forth. What are you going to do with that if you have an n-level oscillator? Right? Is there an easy way to generalize the things that we've learned? And how do we benchmark those things that we learn how to benchmark for 2-level systems? So at the basic mathematics level, you start off with the poly group, but you must change your group. It's no longer SU2. Right? So you must go to a larger group. And there are many ways to look at SUN in the special unitary group of n dimension. But the Weil-Heisenberg group is one example of how to parameterize that. And it gives you something that's rather intuitive. So there are X gates and Z gates, right? You would do rotations and flips, let's say for a qubit. And the idea is when you go from 0 to 1, so on and so forth, now you go ahead and do this over the entire set. So this is the generalization of an X gate over this larger group. And a Z gate is actually quite elegant. Normally, you're thinking about pi 90s, so on and so forth. Now you just have the n roots of unity that give you this rotation. So I kind of like this. Oops, sorry, I'm hitting the wrong button here. I kind of like this because it sort of generalizes very easy things that are intuitive to you in 2 dimensions. And then, of course, the Hadamard turn takes on this particular flavor, right, in this Weil set. And you can think about how to do control Z. So here's now, for example, an X flip that's conditional on a Z. And if you want to do a C naught, then it's a combination of this control Z and Hadamard. Okay, so that whole logic is there. This is just to point out that we can extend many of the things, if not all of the things that we've understood for qubits and quantum information processing to n-level oscillators. Okay, so the plan for today going forward is as follows. I think I can make this thing go away. Maybe. Okay. We're going to talk about first the type of interactions and couplings that you have in the rest frame. This is the ordinary thing. Here are 2 pendula. How do I make them talk to each other? And this is really a little bit of a walk through history, because this is, in fact, the cross-resonance effect, the cross-resonance gate, so on and so forth. And these things are still used in different flavors. But I wanted to show you how we've extended them and what are some of the limitations in this particular methodology. So here, I'm going to go ahead. So here are my 2 pendula. And you can see I've coupled them with a little bit of a spring in between. And the idea is I drive either one of them or 2 of them on resonance or off resonance, and something will happen, right, with the coupling between them. Okay, then after that, I want to show you something where, in fact, I go into a rotating frame and bring different levels onto resonance. And this will allow me to either have an XY exchange interaction or a spin interaction. And you can see here, I just wanted to write down, we had to work actually quite hard to get decent gate fidelity in this, getting close to 3 nines. If I do this in the rotating frame or the Floquet frame, I can make all of these states in one go, which are many body states, atomic Schrodinger-Cat states, control Z gates with reasonably high fidelity. And all of these things, if you try to extend the static lab picture, are extremely difficult to do. So that's sort of the extended outline for the next 15 to 20 minutes. Okay, so let's talk about this first vanilla-based coupling in the lab frame. So it starts like this. You have two pendula. The one has a frequency called omega control. The other physical pendula has a frequency called omega target. Okay? And what I'm going to do is I'm going to look at the oscillations on omega target as a function of what I drive on the control. Okay? So the control frequency is here. So this is a filter function. If I put my finger here and drive this system at this frequency, you see this is off resonance. This is why it's called cross resonance. I'm driving this pendula, which would like to be driven at omega c, but at the frequency of this one, omega target. So not much gets across. And in fact, when omega c is close to omega target, yes, then I have a lot of amplitude which is transmitted. Right? So very little is transmitted of this drive amplitude here. Okay, right? But the population nevertheless rotates. Now here's the quantum piece. If I change this oscillator from 0 to 1, I change the filter function. Right? You see the frequency changes. So now I have a very different amplitude coming through, whether this qubit is in state 0 or state 1, whether I'm in the ground state of this n-body oscillator or the 1 state. Okay, and so the oscillations then become out of phase. And if you look at the right spot, then they will be 180 degrees out of phase, and you have a C naught. Okay, so that's the recipe, for example, of getting a cross-resonance oscillation, is just pushing a pendulum out of phase. Okay, the problem is you have to tune all of these parameters correctly, right? Because you see it's narrow, the Q matters, the detuning matters, the drive frequency matters, so on and so forth. Moreover, there's always an on-ZZ coupling between these things, which is problematic, as many of us know in the field, to deal with. It makes this hard. So in addition to tuning these critical parameters, you don't have a lot of handles. So one of the things we did with Brad Mitchell some years ago was to say, well, what if you just drive both pendula? Right? You can get more knobs in that particular case. So here, I want to familiarize ourselves with this type of level diagram. This represents the global ground state, both of the control and the target, right? That's the 0, 0 state that's here. This is one excitation in both systems, right? In the first qubit and the second qubit. Okay, and this is the ladder, right? This is 0, 0, putting one excitation in the first qubit, two excitation in the first qubit, so that's omega c, right? And there's omega target. That's the excitation in the other qubit, and they don't have the same frequency, right? So those levels don't line up. You can then think about, well, what's the coupling constant J between these pairs of levels? And there's a few different elements that enter there. So delta is the detuning, right? That's the detuning between the frequencies of these two qubits. Don't worry about the eta, but it's enharmonic, so you should need to put in the enharmonicity there to get the right levels. And then one thinks about how do I actually get these things to talk to each other? Well, I'm just going to look at the difference between the levels, 1, 1, 0, 0, and then, of course, this 0, 1, 1, 0. Right? This gives me the effective strength of the interaction between these levels. If you're a quantum expert, what's happening is what I showed you in the previous case was basically a ZX interaction. I showed you a C0 gate. So that ZX interaction has some coupling strength at which you can write in terms of these coupling constants. And that's what I'm doing here. This is the ZX interaction rate, or the ZZ rate, which is here. So to first order, it looks like this James Cumming physics, right? You have J squared over delta, right? In this dispersive limit. That's the coupling that's there. The second order term is basically what I get from this induced Stark shift. I go ahead and drive the system like I drive an atom, so the frequency is going to move, right? And as that frequency moves, I can move it in and out of resonance. So the utility here is if I drive both sides, then I have a pair of terms. This is now third order, right? J epsilon epsilon. Epsilon is the drive amplitude. Delta is the detuning. So it's the next order term, but I have it both for the drive and for the target, which means I can also change its sign. That's actually really useful. So when I change its sign, I can cancel the static ZZ interaction. So I can really turn the gate off, as I told you. So that's useful. And number two, I can crank up the amplitude very high of this interaction. Normally, it's not very strong. I can actually make it much stronger than the other terms of the problem. So this allowed us to benchmark a gate very cleanly with 994 fidelity many years ago. So it's gone above that. So the utility of this, again, is that you need more knobs. You don't need to get all the frequencies right. It's a broad range of frequencies. It's a type of if you like. It's not parametric yet. I'm sort of coupling them in the real frame. But you start to see adding more knobs is useful, even though you think that it may be difficult to have more experimental handles. So how do you do this for more than 2 levels? So this is starting to get to things that are a bit more recent. So you can have Qtrits. Okay? So Qtrits, of course, have 3 levels. This is just the generalization into more terms of the Jaynes-Cummings Hamiltonian that I wrote. So now you have your 3 levels, and you have coefficients that couple all of these 3. And you see this has the same flavor of that DZ interaction that I wrote. Right? It's the difference between pairs of energy levels in some 2-level manifold. So the task at hand is how do you measure all these coefficients? It's actually quite difficult to do that a priori because there's a lot of them. And they grow very rapidly as your Hilbert space gets bigger. So the idea is, again, let's drive again, both pendulum, both oscillators, right? So this differential stock shift, if you like. So then now you have these coefficients alpha, but you also have drives, capital omega. So basically the task at hand is to have smaller fingers. But how to drive this alpha, right, with something that's a function of the frequency, the phase between the drives and the amplitude. Right? So I need to figure out these coefficients. So you set up a pulse sequence for doing this, and the 2 dependencies you want to pull out is that this alpha coefficients depend on the relative phase difference of your drives, and they do. Right? So here's the experimental data showing you that as a function of phase for the different coefficients, 1, 1, 1, 2, 2, 1, 2, 2, so on and so forth. And also they should be quadratic, after all, it's a stock shift, should be quadratic in amplitude. And you see this quadratic dependence, which is there. And you can fit all of these parameters, if you like, with some Q-tip simulation to make sure it's working. So this allows you to make a very good gate. Okay, this generalization of this cross resonance to 3 levels. And there is a science to how to benchmark 3 levels. Right? So in fact, what's the set over which all the Cliffords that you check this, how do you, so on and so forth. Again, something we can discuss in the discussion session if you like, but we had to sort of think about how to come up with the right benchmarking technique for a gate which is no longer a qubit gate. We can do this in 2 ways with, for experts, this in the QIS field. We can do this with cross-entropy benchmarking. Right? This was first shown by Google in their experiment. We can also do it by cycle benchmarking. Okay? But nonetheless, you can see the point of this slide is the fidelity is starting to get really good. Right? Even in 3-level gates, we've done even much better than this now. Okay, so how do you go beyond this, right? How do you go beyond this? Because you see, this is not a very scalable scheme. If I try to go ahead and have 4 levels, then there's more coefficients, and I have to tune all the coefficients and so on and so forth, right? It was already hard enough with 3. So I want to go into this idea of, well, let's not think about static qubits in the fixed frame, a laboratory frame, but let's go to now the Floquet frame or driven qubits. So this story started looking back at least in 2012, not before when Cater Murch was still in our lab. So that experiment that we started to think about was what was at that time called bath engineering. Right? You want to actually go ahead and couple your qubit to some bath or some Louisvillian that you can go ahead and relax or excite the qubit. This was well known to the physicists that worked on cantilevers and oscillators. This was the cooling with sidebands. All optical mechanics people knew this quite well, but it really hadn't been shown in the superconducting domain. So the idea was, let's take a qubit that has energy levels ground and excited, shown here by G and D. We're going to go ahead and excite this qubit at omega q. So you're going to Rabi flop it, right? So if you go to the dressed frame, or the frame that rotates at this frequency, it will appear to be an effective qubit whose splitting is the Rabi frequency. Okay? So let's imagine we're flopping this at of order 10% the rate. This can be 10 megahertz, 20 megahertz, so on and so forth, on a qubit which is several gigahertz wide. Now, what we did was we coupled this qubit to a cavity, which was either driven with a red sideband or a blue sideband. And the simple idea being that if you drive these 2 tones now, 1 tone on resonance to do the flopping, a 2nd tone at omega d, the difference between those 2 frequencies will have either a red sideband or a blue sideband. The red sideband will actually pump photons into the qubit and heat it up. The blue sideband in this case will be an anti-Stokes process. The photon will come out, and if you line that frequency with the resonance of your qubit, you prefer the blue over the red, right? Because red photons can't get in and out. So you can preferentially heat or cool your qubit on demand to produce either the plus or the minus state. Okay. So in this particular case, we wanted to enhance coherence of the system because lifetimes 12 years ago were not so good. Okay. So we went ahead and tried to do a Ramsey experiment, where in this bare qubit, we had 5 microsecond lifetime and only 40% contrast, meaning you weren't really not polarizing your qubit in the ground state. There was no concept of heralding or what have you at that time. So basically we had limited contrast, but now what we could do is we could just park, right, using this cooling, and then see what would happen to the Ramsey, and we can have it Ramsey, have these Ramsey oscillations for as long as you want, right? We can go ahead and just park the qubit. So this is now millisecond on the horizontal axis. So this gave us a sense that you can park quantum systems by interacting them with a cavity, by adding photons, so on and so forth. So this was, again, bath engineering to stabilize coherence, but then you start to think about, well, can I use it to perform a gate operation? And you see the ion trappers have done this forever, right? So the workhorse gate, at least to my knowledge still up till now, is this Molmer-Sorensen gate. Okay. And the idea with this gate is if I have two ionic systems, and I couple them to vibrational modes. After all, they're in a trap that moves around. The ion system has, let's say, in this particular pair of transitions, some 10 gigahertz transition. The phonons are sort of separated by 5 megahertz in this phononic spectrum. So again, the same type of diagram, GG, both in the ground state, both in the excited state, with n vibrational excitations. By the way, you cannot typically go from GG to EE because of parity forbidden. Otherwise, you would just drive that transition. So here, now I have the manifold of states of one excitation in one ion, say, one excitation in the other ion, looking at n phononic excitations, or n plus 1 or n minus 1, right? And this spacing is kind of obvious. This is 5 megahertz, and this is much bigger. That's here. So you drive these transitions, which are really virtual transitions, right? You drive off resonance, okay? And that couples this state to here with a beam which is detuned in the red and in the blue, just like I showed you, okay? And you do it on the other side as well. And if you go halfway, you will entangle this state EG plus GE. And that's how you create at half excitation this entangled state. And for the ion folks, if you have many ions, you just extend this manifold. They all talk to the same vibrational mode, and you can create this n-body entanglement. That's there. So we thought, well, this is very similar to what we were doing, right? We're driving the sidebands. Maybe we can do it for superconducting qubits. So the first thing to realize is we have to invert the scales, right? For us, the qubit is also like 10-ish gigahertz. The cavity also 10-ish gigahertz. So you don't really have this low frequency bosonic mode to do this. But the qubit that I showed you where I Rabi flopped it is a low frequency qubit, right? So in fact, you just invert this level diagram, right? The qubit spacing now is low frequency. There's tens of megahertz. The cavity is this 10 gigahertz. And you can run this Molmer-Sorensen business again and create a 3-qubit GHZ state, a 4-qubit GHZ state, so on and so forth. So this was done again still a few years ago. Super hard experiment, super hard. Took multiple years, at least 1.5 PhD students, right? Because you have to park the right resonance conditions. Ions are deity given. They all have the same frequency. Superconducting qubits do not, right? All the kappas are different. All the chis are different. Plus the loss of the resonator, which is really painful, will kill your all of this, so on and so forth. So after sweating blood, even with 4, we only got 66% entanglement. And then we gave up, said no more with this. And that's really the final piece of the story that I want to get to. Well, what if you actually go in the driven frame? We're already in the driven frame. Can you do the operations in the driven frame? And they're tremendously easy. And they realize things that the superconducting community has done, right, with parametric couplers, with tunable qubits, tunable couplers, so on and so forth, to get these XY type interactions. Okay, so just to spend only 5 minutes or so, then we can go to questions. The idea is I have my qubit, right, and I drive it periodically. So the sigma z now has a periodically driven sigma x term, which is here. The Schrodinger equation, which we're all familiar with, is written here. But in fact, if you have a general time-driven problem, the solution is not obvious, if not attainable at all. However, just like the solid state people know, if you have something which is periodic, you can look for things that look like block states and block waves, right? In general, these are Floquet states that will have this periodicity. The Floquet wave functions are here. They're periodic up to certain wave vectors. And the energies also become a spectrum which is periodic within the bare energies. So it looks like a Schrodinger equation. There's a wave function, but it has some periodicity, and there's some energy which also has some periodicity. The utility of this is depending on the frequency that I drive, right? There's a natural frequency here for the qubit, omega q, and the frequency for the drive, omega d, as I showed you in the previous slide. If I change this detuning, you can see I can change the energy by a lot, right, of that Floquet qubit. That's handy. And if I want to get things to be on resonance, okay? And I can also play with the drive amplitude to also change the energy. So I can do all of these Stark shift kind of tricks, right, that were there, but now in the Floquet frame. So again, time periodic Hamiltonian quasi-energy states and quasi-energies which are tuned by detuning and amplitude. Okay. So now what I need to do is go into this Floquet frame, do whatever I need to do to entangle them and come back out. But I need to do it fast. The problem is I don't want to have Landau-Zener transitions to all the other states. So here's where I start to use dynamical decoupling, all sorts of flavors of tricks. So I have some fast pulse, which takes me from, let's say, 0 into the 0 in the Floquet frame, the 1 in the rest frame here into the Floquet frame. And I want to see what happens when I try to map 0 to 0, how much of the 1 do I generate? So I do that here, showing you a 30 nanosecond pulse to a 75 nanosecond pulse. So I'm trying to map 0 to 0. This is the population of 1. You see at 30 nanoseconds, I got 10% population in 1. Right? That's the Landau-Zener rate going into the other ones. So I can look at this as a function of both ramp time and amplitude and so on and so forth. So I want to have a long ramp time and low frequencies, right? That gives me very little poisoning. However, if I do a simple drag pulse, just add one component, I can do this 30 nanosecond thing very rapidly. Okay, so now I have a fast way to actually go ahead into this rotating frame and out of the rotating frame. So then the two interactions that I want to have, I have this level diagram. If I bring the two levels into resonance, that's one type of interaction. If I leave an energy gap and drive that gap, right, that's the XY interaction that you have, and this is just the ZZ interaction. So you can see here, I can tune both XY and ZZ independently. So here I turn the XY off, and I look at the dependence on the ZZ rate. Here I turn the XY on, and I still measure the same ZZ rate. So that's nice, right? These things are not coupled together. I can tune any flavor of Heisenberg Hamiltonian that I wish. Okay? And the chevrons, you can see, it's very high fidelity, super clean. So if you wanted, again, put this in the language of gates, this Hamiltonian has several limits. If you want XX, that's a I swap gate. If you want ZZ, that's a control Z gate. And if you want all three terms, right, that's a generalized swap gate. And you can make all three of them and benchmark all three of them with that fidelity out of the box without tuning anything. And you can see we were sweating blood, right, trying to get those interactions in this Mulmer-Sorensen type of gate to work. It's a heck of a lot easier. Then finally, can we do this Mulmer-Sorensen interaction in this driven frame? And it turns out to be much easier. We don't even need the phononic system. Actually, you can just go through virtual states. And they're actually very efficient to go through this. Right? So the idea here is I do the same thing, but now I just drive this virtual transition. There is no phononic mode there, but I use the same kind of idea. And you may think, well, the rate for this will be very bad because you're in this virtual state. You've limited your phase space, but actually it's not that. You're actually going to a quasi-continuum. So in fact, there are many states that you can couple there, and that gives the speed back to the interaction. That I think we had not appreciated when we started this. So again, you can drive things at this megahertz frequency, and there's some equations here. I put them up because you'll have the slides. They look similar to the previous ones I showed you. And the transition rate's a little bit different, but it's still this G squared over delta type of dependence. Okay, and now I can swap from 0, 0 to 1, 1 to 2, 2, so on and so forth, no problem. And in fact, what's interesting is you'll look at this swap where I try to go into 1, 1. You see some parts of the excitation are missing. That's because the coherence is so good, it crosses the other level. So if I pump the other 0, 2 level out, I will actually recover the population. So it's actually hanging out here. The other half of this graph is actually here in 0, 2. So the coherence are so good, you can move anywhere in this space with very high fidelity. Okay, and then you can start to think about, well, how do I get 2, 3, 4, 5, so on and so forth of these things entangled? Here's now 2 Qudits together, and that's real data. There are no more other skyscrapers in between your buildings there. Better, right? There's 0, 0, 1, 1, 2, 2, right? There's the 3, right? And here's the fidelity. That's on the scale from 98% to 1 as you increase the dimension of your Hilbert space. Okay, can you move entanglement around? Here's a 2D grid, right? I'm just going to go through all the animation here. So you start to make this state, which is a heck of a lot more complicated than the previous ones, with still decent fidelity, some work to be done. Okay. So again, showing you ways to create interesting states for sensing. There are folks here, Hideo, you're here, we think a lot about this, beating the Heisenberg limit and so on and so forth. So can we do that with Bell states, Noon states, atomic Schrodinger-Cas states, all of these things? This is real data. You can make all of these states, right, with pretty decent fidelity. One can also think about error correction, Mazir, maybe with this atomic Schrodinger-Cat state. We don't know a lot about this, but there is at least one paper that thinks about this. These are a lot easier for us to make than Kerr-Cat states and so on and so forth. So anyway, if you combine these three pieces together, and this is why I showed you the cross-Kerr Hamiltonian in the beginning, then in fact you can create arbitrary type many-body gates. So control Z, control Z, so on and so forth, Toffoli gates, so on and so forth. So here's a 4-qubit Toffoli with very high fidelity as you combine these elements. So anyway, that was sort of the flavor, saying that somehow when you have more knobs in this driven frame, there are different types of resonant conditions and Raman conditions that you may be able to access that allows you, at least in the quantum information sense, to have better gates, but also just in the many-body physics sense, allows you to move around this Hilbert space that's there. And perhaps if we put all of these things together, we can get out of the range of classical disadvantage to quantum disadvantage, where we don't have to do 10,000 times more operations for one quantum operation and actually get some utility. So with that, I wanted to stop with some ample time for questions. Thank you. Or early lunch, as your preference may be.
Any questions?
Yeah, I think the folks on Zoom probably can't hear without it.
Hello? Okay, great. So my question is, as you extend this thing in Qudit formalism, as you increase the number d, right? Like in the limit of d going to infinity, you should reach the limit of continuous variable system. While I kind of have a hard time kind of digesting in my head how that transition occurs in the picture that you have presented. So can you kind of give some insights on how we can kind of think about continuous variable systems in this kind of framework?
We have a true theorist here. Mazir may have a better answer than I do on this. But as you go to more levels, so on and so forth, you will, of course, then be able to encode things that are in a different quantum number, right? So the normal way I would think about it is if you quantize, let's say, number and phase, right? These are states of a definite number. If you're in some Gaussian type optic system, you're in states of definite phase, say. So I think you will start to get more and more superpositions, right? I showed you the generalization of the X gate. It's over this whole Hilbert space. So your gates will transform, in my mind, to gates that act on states of definite phase. That's the way I would think about it, but I don't know, maybe you ask a real theorist. I taught quantum field theory, but I don't know that question. Ask a real theorist in quantum information science.
Yeah, I just had a question. So, the Qudits are cool because you're right. You can you grow your Hilbert space much faster, and at least for certain classes of operations, you can do them much more efficiently, kind of natively. And I was just kind of curious how, ideally we have no dissipation, and that's great. I was kind of curious how dissipation comes in, right? Because it's now kind of, I could see positive and potentially negative aspects to it, right? Because it's more constrained. Also, there's more rules about how it can happen, but also, of course, as you go up, it grows and things like that. So I was just kind of curious what your
well,
thought about
that's a
that.
great question, and the detailed answer to that depends also on the physicality of the system that you use, right? Because harmonic oscillators have a line width that grows to some quadratic number as you go higher in level. The Transmon qubit is a little bit interesting, right? Because as you increase EJ over C, the bands, as you well know, the bands become flatter, but you couple in more charge elements that are there. So somehow you can still have this polynomial trade-off between coupling and flatness. And the same thing enters into the relaxation, right? It's that same coupling that sets the lifetimes. So in this particular case, for a Transmon qubit, for a modest increase in EJ over C, let's say between 50 to 70, right? Going from that number, the third level will be perfectly stable, okay? And so will the fourth, or slightly more. But I don't think I can go beyond that, okay, in this kind of pure Transmon system. Now, Mikhail Bloch has a very different system, right? Starting off with something that's more bosonic, and he's got like 12 levels, right? Because in a cavity, you can have many more levels as you move around. So it's not obvious, right? It depends a little bit on the physical system, right? But for the Transmon, you will get to 4 or 5, or at least 3, 4, or 5 without very much difficulty, right? And the lifetimes will be good, right? Tens of microseconds, hundreds of microseconds, no problem. And there are other utilities. For example, if you have a qubit that you want to encode, but actually control the third level very well, your qubit is a really good qubit because you don't have these transitions out of the computational manifold. You control those a lot better. So the one output of this is having a 3-level system, you have a really good 2-level system, okay? And moreover, I can actually use and condition operations on the population of the third level. I can use that third level if I want an offset charge sensitive transmon and use that as a sensor for the charge noise that I have there. That's actually useful functionality. On the same site as your qubit, you have a charge sensor, right, which you can use in a feedback experiment or something else. So there are a lot of different ways that this can come in handy, even if you just stay within the qubit manifold, because you have an ancillary level. On the quantum information side, if you want to do error correction a la surface code, then most of your resources are getting into generating magic states and so on and so forth. So if you try to do this with a third level, at least the proposal is it can be a lot easier. We have not pursued this or probed this, but there are, again, more quantum information functionalities by having this third level. So the short answer is I'm not in the limit that gentleman was talking about of going to many, many levels. I'm just extending just a few levels. But since it's d to the n, you actually win even at like 50 elements, you see a pretty big difference.
Yep. Yeah, thanks for the talk. Sorry, I'm not familiar with this work, so my question is probably poorly motivated. But I don't understand why you have to turn on and off the Floquet driving. Is there some, like, can you stay in the Floquet basis and do all the gates? Or
one could, right, in principle do that. But in fact, I'm trying to get the qubit which has a large gap that's there. So I'm just turning it on for the interaction. Okay, so I still have the static qubits and all the benchmarking, what have you. I just want to go to a rotating frame so that they talk to each other. If I leave it there, then I have a very low frequency qubit, right? And if I leave it there for a long period of time, I have a 10 megahertz qubit, and you may have to do a lot more, right, to stabilize that or put it in the ground state or herald it or do other things. So I just go there, come back up.
And then I had another question, which is if, let's say you were trying to just optimize your gates, and you were looking at all the possible ways you can drive the system to do these gates, would you discover these types of gates? Can I just think of these as being fancy gates, or?
I think it's a matter of language, yes. So this is, for example, a Raman assisted whatever gate, right? But in reality, I think it's basically Floquet interaction. And there is now in the literature quite a lot of discussion, right? Floquet qubits and how to do all of these things, so on and so forth. So I wanted to put it in that context. But again, it's the same thing that different communities have called different terms over the years. For us in 2012, this was bath engineering to drive the external system. For Akan Tarichi, this is Leuvillian engineering, right? Turn the bath into something that actually drives your system. For folks that work on trajectories like Howard Wiseman, this is quantum steering. He's at the outside. So I think it's just a matter of language, but the idea is you're going into some place where the environment is more controllable by you.
Any other questions?
I'm trying to understand how do you, I mean, is it some other way of seeing a parametric gate, or that by going in a Floquet picture and
So a parametric gate, say, right, you would basically have still the interaction is between the two static systems, right? I'm just driving at the difference frequency between them, right? Now my qubits are actually are wheels which are turning, right? In the static gate, I'm just driving the two wheels that are different after there's some indifference, so on and so forth, right, to get them to talk to each other. But now I've actually turned the wheels. Right, so it's a bit different.
and also how scalable would that be? I mean, the fact that you're turning on and off this basically rotation of the qubit, and you have many of these, aren't you worried that you might have crosstalk because of these frequencies?
So this is a good question. So I think it's no different, no worse than any other driving scheme. You'll still have to do that. It was terrible in the Mulmer-Sorensen one, because you see the drive stabilizes the frequency of your qubit. So any noise on your drive completely hoses you, right, at the level of 4 nines. And in fact, there was a year where we were just putting these generators in like thermal cooled racks and like, fanning air on so on and so forth, because it directly affects your fidelity. Here it's not a problem, right? Because you need to turn on a pulse and just find a resonance condition over a short period of time. So delta E, delta T is your friend, right, in this case. Right? It's the opposite limit of what you're saying. I want to do it fast and I have a large energy uncertainty. So it's easy to couple these things. So in terms of wire count, no different than parametric or what have you. Flux is worse, right? You need to have even more control lines. This is all microwave. But in terms of stability, scalability, tunability, precision, it's quite forgiving.
Mainly worried about crosstalk of the.
So crosstalk comes in 2 flavors, right? So there's the classical crosstalk that you have between your lines, so on and so forth. And it will kill any qubit at the moment. And I have thoughts about what we would like to do to fix that. So this is no different. After all, even if you drove just a standard parametric gate or whatever, you still have the same number of wires, roughly speaking. So that's that. The quantum crosstalk is sort of more subtle subject, right? Do you have these things talk together because of residual terms in your Hamiltonian? All those residual terms are there in all of these qubits, whether it's a ZZ term or some other higher order term. The nice thing about this is a sign in the problem. I can turn them all off, right? So assuming that they do not fluctuate in time, right, I can tune them in one go and fix them. The cross terms that are quantum and change in time, say due to two-level systems, are terrible for all of us. No better in this or no worse. Maybe slightly better, because if your interaction, to your question, is in the 10 megahertz window rather than the gigahertz window, maybe.
Yeah, we still got about 15 minutes before the official lunchtime in case there's any more.
So I'm talking from the optics photonics perspective here. So that Raman system is not a true Raman transition, but from what I would look at it is a four-way mixing kind of that you've created there, and this is analogous to the dress states that's been done. Is that, I just want to confirm.
It's a virtual Raman transitions, dress states, four-way mixing. That's exactly why I put it there, because I knew you would talk about 3 and 4-way mixing in the morning.
Okay, and so I just want to say, because that's really powerful, which I hadn't thought about, at least from the photonics part, is that it allows you to get around the coherence and kind of make it almost as long as you want. Is that correct?
Yeah, that's basically what we're trying to do. The other thing that it lets you do is you see, we are parity forbidden, at least in this. Different systems have different quantum mechanical selection rules, but at least in this particular qubit, you cannot go 0, 0 to 1, 1 to 2, 2, so on and so forth, right? And the coherence times are short. So if the usual way is to have some kind of swap network, right? So I have a bunch of qubits around, so let's put this one in one and tell the neighbor and so on and so forth. And by the time you're sort of creating that array, finish creating that array, your fidelity is quite poor, right? And quite often in all of these graphs, you see very poor fidelity, because when you decompose that very complicated n-body operation into native gates or hardware efficient gates, it's like 1,000 of them, right, to go do that. But if I can climb as I go straight 1, 1 to nn, I can create very fast, these kind of very entangled states. And it's also useful for metrology. I'll make this noon state, I'll let John Dowling, right, to go ahead and do this. I don't need to lose all my coherence in doing that. All right, so I'm not an optics guy. I hope that was useful. I mean, I'm a microwave optics guy, so Amir may have words on that, but
what I'm looking for is ways that we can take the ideas that you've benefit from that, but I'm not sure people have talked about it in the same way in the quantum optics community, that it allows you to extend coherence, or allows you to have these high order bits or whatever that can extend coherence. And so that's kind of.
we'd also like to learn from you. That's really why I'm here. So please do tell us things that we should be doing.
What's in the Floquet picture, what's like the speed limit? What's the thing you have to be slow compared to?
Okay, very good. So
Like, it seems that your Rabi rates are not 100 megahertz, because I guess still 0, 1, and 2 mixing.
right, that's right. So again, somewhat dependent on the particular system. If you were to do this with Fluxonia, it may be a bit different. There's a general scheme. But at least in the Transmon qubit, the anharmonicity will certainly set a speed limit, right, for how fast you can Rabi flop. So hence the tens of megahertz. Can you Rabi flop close to the transition frequency with some other pulse sequence? Maybe. Don't know. Never tried it. But sort of doing nothing, you take 1/10 of that frequency and you get your Rabi frequency. So that sets the frequency of your qubit, of your Floquet qubit, and that sets the time for a drag pulse, right? So this is at tens of megahertz, but it may not be the limit. Clearly, the anharmonicity will be the maximum limit. But how close you can get to that, I don't know. We are trying to do this with Fluxonium. If we can actually get our Fluxonium qubits to have large coherence, which we are failing at the moment. But if you're able to do that, then you would get very large detuning. Can you do this with cat qubits? I don't know. That's actually interesting, right? Because you're driving already some 2-photon transition in the Hamiltonian. It's already in some rotating frame. Can you come up with a more powerful gate for doing that? We were recently playing around with a protected X gate. It's not so easy to do. And it has some elements of this physics in there.
All right, any more last questions? All right, well, let's thank Professor Siddiqi once more. All right, and we'll take off just a little bit early for lunch in the courtyard and then be back here by 1:45 p.m.